Well, hello friends, welcome back to emulator hacking. Today we're going to continue working on the memory debugging stuff. So the last thing we did was add use after free detection to the x86 emulator. So now if we run our little program that use after freeze, we can get these big error messages here on the debugger, just telling us that we're doing an invalid 1 byte write at some address and blah blah blah, because the memory has already been freed. So the test program that we made for this is this little guy right here. So it mallocs some memory, puts a string in it, and frees it, and then tries to access it and printf it. And these things here are what we're seeing complaints about. So that's fantastic. Now, the next thing that we're going to do today is we're going to catch leaks. So we want, when the program exits, we want to print a report of any remaining unfreed malloc allocations that that are not pointed to by anyone, basically. And then you could argue that, like, on exit you should free everything, but in practice that's kind of a waste of time often, because if you're just going to exit anyway, like, why do a whole bunch of housekeeping work? Anyway, so I'm not exactly sure what the strategy is going to be for that, but we'll start by just making some kind of leak detection. So we have a leak right here. We should be able to catch this one. So let's see what we can do for that. I guess the first thing we want to do is just print something when we exit. So in the exec loop here, it loops until we set shutdown to true. So we can just, I guess we can do something here. How about if malloc tracer? So if we have a malloc tracer attached, then we will tell it dump leak report or something like that, or report leaks. Somehow I like that one better. It's a bit more imperative sounding. Okay, so we'll add something to malloc tracer called dump leak report. And really this is only relevant when we're exiting, right? Because I mean, I guess technically you could report leaks at any time, but right now we'll only do it on exit. And we'll think about ways to do that at arbitrary times later. So, okay, so we're calling dump leak report, and in malloc tracer, now we just need to implement this. Dump leak report. All right. So, how do we figure this out? So we have a set of allocations called mallocations. So mallocations, and we want to, for each one of these, we want to figure out, is this allocation still reachable? So I think for that we will say something like if is reachable mallocation continue. Otherwise, we'll print like one of these nice little things, leak. Okay, so let's see. I guess mallocation size, mallocation address, and then probably what we're going to want a stack as well. But we'll skip the stack part right now because we don't have a way to record stacks. For now, let's just make sure that we can actually print this out. So is reachable. So let's see. So if mallocation is if mallocation is already freed, then it's fine. We don't need to look any further. So we'll just say continue. Okay, and then here we can have a counter as well. Leaks found. Plus leaks found. And then at the end we can print something like Wait, how many spaces are there? 1, 2, 3. Gotta make it look right. Zoo leak is found. Right, that will be our little thing. Okay, so leaks found, and that's that. Okay, and then we need to implement is reachable. Now, what does this thing actually do? I don't know yet. We'll figure it out. Okay. So, I guess the first thing is we can just assert that it's not freed, just to make sure that we're here in a sane state. I don't know. And then, okay, so let's just return true for now, and then we'll see what the report looks like. I postpone figuring this out for a few seconds, just to check the visual aspect of things. So there should be a leak at the very end of running. I mean, a report at the very end of running the emulator when we exit. So that's a very large number. I feel like I didn't set that up correctly. There we go. So mallocation freed is, oh, if it is reachable. Oh, right. We were supposed to say false. Okay, well, fixing important bugs here. Also, oh, this is a bit inconsistent. We have 2 spaces here. Okay, we are fixing these space issues here at the same time. But anyway, that's about as much as I don't want to avoid dealing with it anymore. So let's just get started. So leak. We have 2 mallocations on exit. I guess that's fine, and allocation at. So that's a bit weird that we have 2 at the same address. I don't know what that's about. Oh, no, that's not the same address. Okay, so UAF CPP. This thing actually has a 1 kilobyte allocation. That's probably from std.io. I'm guessing that it's a std.io file. How big is this thing? The buffer is, how large are you? Well, I don't know, but I feel like that's what it is. Okay, so once we get the stacks, we'll be able to see what that is. So how do we determine now that these things are reachable or not? So basically, we're going to have to scan all of our memory and look for the address anywhere in memory, essentially. Or in the case of mallocations, we have to look in all active other mallocations and see if they point at this one. So basically, look in all other mallocations. That'll be something like if, oh wait, hold on, other mallocation. So if these are the same, of course we'll ignore, we don't want to look in ourself. If you point to yourself, let's say that's still a leak. Okay, and then we just need to scan through this allocation for the pointer. So I got caught thinking here, like, what if you have a pointer into the middle of an allocation? But I'm gonna say that in that case, for now, let's consider that still a leak. So if you allocate something and you allocate a buffer and you have a pointer somewhere that points into the middle of your buffer, but nothing that points at the head of the buffer, like that, nothing that points at the thing that you would have to pass to free. Let's consider that a leak as well. There are some situations where that might be valid, but let's not deal with that right now. Let's only look for the 0th index in the allocation. So I guess here we'll start with something like we'll just treat the allocation as an array of uint putters. So let's see. Allocation as putters is a reinterpret cast to uint putter t star allocation. Oh, wait. This is this is in VM, right? So this is not in host memory, but in the virtual memory, right? So we have to access it a little bit in a roundabout way. We have to use the emulator, the MMU, read 32. This actually makes it not so bad. Okay, so let's compute how many pointers in allocation is mallocation size divided by, that's just divided by the size of a pointer, which is a U32 in our case. So, like, just thinking that, oh, you know, what if we port this thing to 64-bit? But like, that's going to be a lot of stuff to do. This is a 32-bit machine right now, and let's not worry about 64-bit. People often ask me about that, by the way, like, oh, why don't you port to 64-bit? Why isn't Serenity 64-bit? It's because, I don't know, because I don't need it for anything right now, and if we need it for something in the future, we can port it to 64-bit. There are so many things to do that don't require or really benefit from 64-bit. So I just tend to do other stuff first. But at some point, I will run out of things to do, and 64-bit will be the next logical thing. Or somebody else will come and say, oh, I'm going to implement 64-bit support, and we'll get it that way. But either way, it'll happen someday in the future. It's just there are so many things to do right now that I care about way more than 64-bit support. So that's why. So how many pointers? We know that already, so then we just need to iterate. Okay. And value is, let's just say value. Value is read 32 bits from, it's a logical address, so I'm just providing the data segment. And that would be mallocation address plus I times size of U32. All right. And then if value equal mallocation address, then we found a pointer. Return true. Okay. There are most certainly faster ways of doing this. I'm just doing it the naive way to get started, and we don't worry about performance when we do first implementations of things. We worry about performance later. That's the big boy way of doing it. So here we go. These things, both of them still come up, of course, but let's try. Let's print out something here when we find it. So is reachable false. So these should actually be considered unreachable. What if we, I guess let's make another program, a test program, because this one is already printing all these other warnings. So let's just make one called leak CPP. And here we'll do something a bit stupider. And I guess we can add some struct foo. Why is it so hard to type foo? Okay. And maybe we'll have some goof. Yeah. All right, and foo1 is new foo. Foo2 is new foo. Foo1 other is foo2. So now we have two of them, and this one points to the other. But then we, if we free this thing, or no, if we don't free them, they should. Okay. Let's just not free them and see what happens. I just want to see how this print thing comes out. 0 leaks found. All right. Wait, oh, maybe these are optimized out again. Let's not spend 10 minutes figuring out that the optimizer throws these away. Okay, here we go. So very good. So we have two allocations leaked at the end. And then what happens if we delete foo1? Okay, that's gone from there, I guess because it gets marked as freed, actually. We didn't print anything. Oh, I didn't add any prints. Dang it. Mallocation. This is reachable from mallocation P. Okay, and mallocation address, mallocation, other mallocation address. This is what I want to see. Okay, so they're not reachable. Oh shit. Yeah, so here I want to say that that one of them is reachable, right, from the other, which of course is not perfect. Okay, so I'm not doing this right. What am I messing up here? Dump leak report. Is reachable. Oh shit, I should be looking in the other mallocation. What am I even doing? Okay, we are fumbling here a little bit, but not to worry, here we go. All right, so mallocation, this is reachable from other mallocation this. And later on, we should probably construct a graph or something so we can work out if there's like, you know, like a self-contained little graph that just points to each other, but nothing else points to it. But right now, we're just going to do things the easy way, and we will leave those big brain things for the future. So let's see. So these are 2 leaks. And now, I guess we're only looking in mallocations. So this thing here is probably not a leak. We would determine that by not only scanning mallocations, but also scanning data segments and stuff like that. So let's see. So we would need to look in every single block in the MMU. So this is scanning through allocations. Okay. So 1, search in active non-freed allocations for pointers to this allocation. All right. Then 2, search in other memory regions for pointers to this allocation. Okay, so then we need to ask the emulator for a bunch of regions. We ask the MMU for regions. Emulator, the MMU. Can I get to these things? Regions. Wait, what's wrong with this? Must have an initializer. Well, I just want to expose the regions, bruh. So const not null own putter vector regions const return m regions. Oh, if. Okay, that was stupid. Right, it's good to use the right keyword. So here we'll say if region is mmap region, let's say, or is mmap. We got to figure out what these things are, because we really ought to know if like a region represents a malloc chart block or not. So virtual bool is mmap. So if it's an mmap, then we can at least cast it to an mmap region and learn more about it that way. So let's just add something for that. Return true. All right. So if it's mmap and static cast const mmap region. Apparently I don't have mmap region. Okay, so if this mmap region is a malloc block, then skip it. The thing is that this thing is a bit overly permissive. Right now, it only checks if it's not file backed, so we need to fix that for this to be complete. But outside of that, it should be fine. And then, oh, and we need to also skip stack. We don't care if something's on the stack. Continue. Okay, so that needs to become a thing as well. Is stack, and I guess we don't really have a specific thing for that, so we can just have like, or how do we know that something is a stack? You know what? Let's just have a flag for it. Whatever. And you can even say set stack will be, and stack is b. All right. And then when we set up the stack, So create a region here. We will say stack region, set stack true. All right. And then we don't look in that. Great. Now we got to compute how many pointers in region do we have to look at. And it's almost like maybe we should construct a hash set of every pointer in the region here. That would be one future optimization. I think we'll just skip that over right now, but in the future we'll probably want to create either like a hash set or like a sequence of filters, like maybe like a Bloom filter in front, or I don't know exactly. We'll get to that shit later. Pardon me, but I don't want to optimize up front. So pointers in region is region size divided by the size of AU32. And then we will just scan all of these like good boys. So here we go. Same concept here. Although I guess we can just ask the region directly at this point. Region dot, oh, it's a const. I can't. Well, you know what? You know what? I'm const here too. Well, I don't want to have const access here. So you know what? We are unconsting this. Okay. Now we can read. Because reading and writing are both non-const operations on the MMU, and I set it up that way because usually like if you have read and write something, then it makes sense for read to be const, but when it comes to something like this, we might have all kinds of behaviors that we want to do in a read operation that are not necessarily const or const-ish, so it's easier to just not make it const. Anyway, so we want to read at an offset, so the offset is the I times size of U32. And we want it to read 32, not read 8. Okay. And then if value is mallocation address, then we will say this here is reachable from region and I guess we can print out the region base, region, let's see how we do this, end -1. We'll print out like the address range. That'll be kind of cool. Because I'm thinking that this thing here, which I suspect is stdio, we should determine that this thing is reachable from some region, like the elf executable or whatever. So it's reachable from this, which is suspiciously looking like an elf data segment address. But let's confirm that. So read elf -l. Userland leak. So 8072 through 767 CF, and that is this guy right here, the data segment, read write. That is great. Okay, so let's run it on something else. So now it catches that one leak that we have. Run it on something else, catches all these use after freeze. Oh wait, but then now we're doing the use after free auditing here during the leak report, so we should probably stop auditing at that point. Is in malloc or free. So let's see if audit. Say enabled. So let's see. just have a way to turn this off. True. And then when we get to the leak report, we can just turn it off. So temporary change. Set to false, and then we'll flip back when we return, in case that makes sense. I don't know. Who knows if that would be useful. At least it's good to have a way to turn off the auditing. Otherwise, the leak checking is going to look like this. There's a lot we can do actually to make the leak checking faster. It's like going through the MMU region lookup path is obviously not fast either. So leak catches that thing, and UAF complains about the use after free bugs. And finally, when shutting down, it complains about a leak. Fantastic. And then what if we run some program like id? No leaks found. That's great. And what if we run the user space emulator on echo hello? Then we have other problems. Okay, so now apparently I've broken the ability of the emulator to run itself, which is a bit of a funny problem, but I just need to implement more instructions. Let's not think too much about that now, though. So cat, let's see, pass WD. Oh, that doesn't work either. Oh, right, I have to take the emulator out of the pipeline. Okay, great. Well, at least we don't have like obvious leaks in basic utilities. Let's run the markdown converter. Or maybe we can do man get PID. Oh, we don't have the access syscall. All right. Share man2 pledge. It worked. It had no leaks. Very cool. So this is obviously really neat. But I feel like it would be way cooler if we actually printed the stack that that this allocation was allocated at, because like if we just know that a byte allocation at a certain address was leaked, it's not super actionable, right? So we need to actually know where this comes from. And for that, we need to keep track of stacks. So with a mallocation, let's store a, let's see, we want to store the backtrace, but we don't want to symbolicate the backtrace because that will become a huge performance drain if we have to symbolicate every backtrace that we capture. So let's just capture the addresses, and then if in the future it turns out, okay, this backtrace is actually relevant for something, we can symbolicate it then. So now for simplicity, let's just use vector. Vector of flatper backtrace. In fact, maybe we should have two of them. We should have a malloc backtrace and a free backtrace. Because if an allocation is freed, and then you do a use after free, it's very interesting if you can see that you use after freed in an area that was allocated here and freed here, right? And now you're actually touching it here. So 3 stacks in a UAF. It's very, very helpful information. So actually, you know what? Let's commit this first, what we have here. So do we have any separate things? We have the just marking the stack thing as a stack thing. Let's do that. So is mmap. I'll just add both of those together, yeah. Okay, commit user space. Add a way to check if a region is stack mmap. Add ways. Yeah. Okay, and then let's add the rest. Implement very basic leak checking. Upon exit, the emulator, the emulator will now print a leak report of any malloc allocations that are still live and don't have pointers to their base address anywhere in either another live mallocation or in one of the non-malloc block memory regions. Note that the non-malloc block memory region check is still is not fully functional, and this will work even better once we get that fixed. This is pretty cool. Okay, so let's just do a little bit of alignment work. Great. Next step is the stacks, right? So we put that back. And now when we do a did malloc or did free, we want to capture a backtrace. So let's see how we do that. So let's see, here goes the backtrace. So I guess we'll just ask the emulator to do this for us. Capture raw backtrace maybe. And the free backtrace will be empty. And let's see, when we free something, we'll say mallocation free backtrace is emulator the raw backtrace. Here we go. So that's the start, and then let's go and actually invent this thing. So this will just be a matter of having a variant of this that returns a vector of flat pointers instead. Flat pointer, by the way, is just a type def to like U32 in this case. I just use it in place of actual pointers because it would always be a bug to have like an actual pointer into emulator memory, because we should never dereference a pointer into emulator memory. They're just numbers that refer, they're like indexes into the memory space of the emulator. That's why I use a separate type for them, just to keep things sane. So, right, so let's put this, I don't know, here. And, you know, these could really be const ops, now that I think about it, because they're not mutating anything, right? Yeah, that's what I thought, but they call it read, so you know what? Constness out the window today. Okay, so here, we're just going to do this, except no symbolication, essentially. Flat footer, backtrace, and turn backtrace, or we can break there, and don't symbolicate, instead just put that thing on the backtrace thing. Append, red put. Yeah, there we go. And then we need a way to print these. So we'll have like a way to dump a backtrace when provided with a backtrace. So lat footer backtrace, I guess. So then it's just a matter of, wait, we're forgetting something here. We need to also add the EIP to the top of the backtrace. Otherwise we don't see where we are. Okay, so address and backtrace. And let's see, and then we'll just try to symbolicate. And as long as we can, we will just print it out. Oops, and we shouldn't do EIP, we should do address. Okay, that feels kind of reasonable. In fact, you could even say that this could be written in this way, just to reduce the amount of duplication, right? Dump backtrace, raw backtrace. Wait, why don't you like that? Oh, right, because we didn't declare this. It's a little bit less efficient, I guess, because we create a temporary, but it's not the most important thing in the world. It's nice to keep things separated. So I think maybe we'll do that. We're not going to be dumping backtraces that often, hopefully, because it means we have bugs. Malloc tracer. So what am I forgetting here? I can't append this way because I guess you don't know what this is. So no, that was not it. You don't like this. Okay. Oh, the freed is missing? You're not freed. Dump, backtrace. Oh. I deleted it entirely. That was not my intention. Okay, so just verifying that it still works, printing out backtraces. Yes, they still come out, right. So that's good, but we need to make sure that we actually dump the nice backtrace here. So let's see, in the case of a double free, I'm just thinking, like, in the case of a double free, do we really want to overwrite it with the second thing? I think we don't, so let's do that. Because, yeah, if you're doing a double free, then the first free is the only free stack, free backtrace that matters. Anyway, so okay, so now when we dump the leak report, let's say, I guess here we'll just dump the stack. So emulator the dump backtrace mallocation malloc backtrace. And look at that. That is so cool. So we have a leak, an 8-byte allocation at this address with this allocation stack. It's operator new in main. Frickin' cool. That's really cool. So, like, if we have leaks, we should probably print that out in red, I'm thinking. So we'll do something here. And this will be our color. So if leaks found, then the color will be 31. Otherwise, color will be 32. just to give a little bit of spice to that last statement to make it stick out. See, one leak is found. And this one finds a leak as well. If we run id, 0 leaks found. Very cool. That is very cool. Man, I love it. So this is awesome. Let's commit this, and then let's also improve the use after free stuff, since we now have more stacks. So user space emulator, capture, backtraces on malloc free events. This lets us show backtraces for each leaked mallocation in the leak report at the end of execution. Leak report at the end. Yes. Very cool. Super duper cool, actually. So let's see. I feel like these reachability things, they're kind of overly verbose maybe, so if debug spam, let's put these behind if devs. Let's say debug reachable debugging. Reachable debug. Yeah. Because we're going to want to debug this eventually, probably many times, but I don't want to see it all the time during normal execution, so because it's going to get super noisy the bigger your program, right? So we'll just do this. Put the reachability logging, mallocation reachability logging behind a macro. Memory reachability logging. Yeah, right. So those use after free error messages, let's make them better. So this is where we are right now. So let's see. Do that, and then we can say emulator the dump backtrace. This is where the event happens, and then next step is where did we allocate it from? So do we do allocated first and then freed? I guess that's fine. So mallocation, mallocked, allocated at, later freed at, free backtrace. Dude, this is gonna be so freaking cool. So let's see, use something here. Oops. Let's see how this comes out. We might have to tweak the output a little bit, we'll see. All right, so what are we working with here? So we can see it as a 1 byte write at this address. This is where we are right now, use after free, right? This is our current location. It's 2 bytes into block of size, blah, 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 allocated here, and then freed here. This is awesome. This is like everything that we need to debug use after free problems, right? Because like now we can learn where is the use after free happening, where was the memory allocated, and where was it freed. When we have this information, it's like so much easier to actually figure out what's going wrong, right? Super duper cool. Okay, so And by the way, I was doing a little bit of optimization work since yesterday, and it's now significantly faster. So yesterday, we're running id with all the memory checking. It was like almost took a whole second, but now we're back under 100 milliseconds, so that's good. Very, very, very cool. So let's do a host lookup. No leaks, no problems. This is super nice. And what if the host program would do something dumb? Like say that it would, say that we would just use like a malloc buffer here instead, right? Like no big deal, just a malloc buffer. That we don't free. And then what happens? If we run ue bin host google.com, interesting. Now we have all kinds of problems. So we have a 32-bit allocation leaked. That part seems sane. But the rest of this stuff is suspicious. So what are you doing here? Get host by name is wait, did I shadow something called buffer? No. Oh shit, no, look at that. It's size of buffer. Oh, interesting. Okay, I messed that up. So there was a problem. Yeah, there we go. Okay, so very good for catching mistakes, clearly, and it also catches leaked mallocations on exit. Now, this is obviously not perfect, and there will be many goofy cases where this kind of checking is not good enough, and we need to build up a better understanding of reachability. But just these like naive initial test cases works out, and I think we have the building blocks here to iterate and like support more scenarios. So I think this is going to be really, really, really amazing for debugging. And I can't believe that this project is going so well. Like I'm so happy with the way it's going, because in the past, this kind of stuff always seemed to me like this is too complicated, too advanced, whatever, and I'll let somebody else deal with that. Like I couldn't possibly build this kind of thing. And then for some reason I decided I'm just gonna do it. I think the thing that made me want to do this is that I wanted Valgrind, but I didn't want to port Valgrind because that sounded like, I don't know, uninteresting. And I figured like, all right, fine. I want Valgrind. I don't want to port it. I guess we have to build it. And now we are doing that, and it's going really well, and it's really exciting. And I really hope that this is interesting to people because I don't know, I just really want people to see how these things work and to see that it's possible to build them. I didn't even think it was possible myself a while ago, but here we are. So it's all good. Let's not commit that bug we added to host. So what do we have here? That was just adding those traces to use after free logging, right? User space emulator. Include malloc free back traces in UAF logs. When catching a use after free bug, we now use after free. We now also print out the back traces for where the memory was allocated and for where it was freed. This will be extremely helpful for debugging. Cool. Cool. All right, I think this is going to be it for today's video. So if you made it this far, then thank you for watching. And I really appreciate everyone hanging out and checking out this series. I didn't know how it was going to go when I started it, but like I said, I'm really happy with it. And I'm not sure what we'll do next, but there are many more things we can do, so we'll keep adding interesting and useful things. And at some point we'll probably have to do another passive optimization once it gets too slow again. And then as the emulator core matures, we can test more apps and so on, but all in good time. Anyways, thank you for checking this out. I hope that you saw something cool. I will see you next time. Bye.